it's time for a bonus section here. It's not actually part of the textbook, but it's definitely going to be part of your course next year, so I thought I would include it. It's called Indeterminate Forms and L'Hopital's Rule. So we better start by explaining what indeterminate forms are. You know, when we did limits way back when, and we found that the first strategy to try to solve a limit, to evaluate a limit, was just to substitute right into it, and we hoped that it would work, and often it didn't. And it turns out that when you attempt to solve a limit by substitution, and it leads to an expression without sufficient information, in other words, like it doesn't work, that's called an indeterminate form. So the most common forms, like the most common way this will show up, is that you attempt to simplify or substitute into the limit, and you end up with something like 0 over 0. Or you end up with infinity over infinity. These are the two most common forms of indeterminate forms. Now, not as common, but definitely can show up as well, and also are examples of indeterminate forms, is if you get something like 0 times infinity, or infinity minus infinity, which does not equal 0, or 0 to the 0 power, or 1 to the infinity, or infinity to the 0. All of these things, if there's any of these that you're like, oh, I know what that answer is, you're wrong. We don't know any of these answers. If you end up substituting into a limit and you get any of these things, you're stuck. There's not a single thing you can do. But what you could do is try the other methods we used for evaluating limits, like factoring and multiplying by the conjugate, finding common denominators, all those sorts of things. Or you could use L'Hopital's rule. You could always use L'Hopital's rule if you have indeterminate forms. So first of all, let's try solving this limit without using L'Hopital's rule. So this is just like what we did before. It's a nice review from the start of the year. If we tried to substitute right now into this, we want to know what the limit of this function is x approaches 1. So our first strategy is, well, let's just hope that it works when we plug 1 into here. So let's do that. We plug 1 in here, we get 1 squared minus 1 over 1 squared minus 1. Well, that's 1 minus 1, which is 0, and 1 minus 1 is 0. We get 0, 0. Oh no, we have an indeterminate form here. So substitution didn't work. So what did we learn to do before? Well, one thing we learned to do is to try factoring, and you can factor top and bottom. So the limit of the top will now be x, take out an x, and you're left with x minus 1. On the bottom you have a difference of squares, so you have x minus 1, x plus 1. The nice thing about that is you can cancel this and cancel this, and now you're able to substitute in. So you get, put 1 into the top. On the bottom you have 1 plus 1. So we get the answer 1 over 2. So we haven't learned L'Hopital's rule yet, so we can't use it. But after I teach it to you, you'll come back and solve the same one by using L'Hopital's rule, and you'll see you'll get the same answer, 1 over 2. Okay, more review here of limits just to get ourselves up to speed here. So again, let's just try substituting here and see what we get. So this is as x approaches infinity. So what we would have is infinity squared, I know that's weird, minus 1 over 2 times infinity squared plus 1. Well, infinity squared, that's still infinity. Take away 1, you're still at infinity. Infinity squared is infinity, times 2 is infinity, plus 1, you're still at infinity. So you get infinity over infinity, which is indeterminate again. So you're going to have to use a different form. So one thing you could try to do is factor here. But if you do that, you can't factor the bottom. And all you'd have at the top is x plus 1, x minus 1. Can't do anything there. So what are you going to do? Well, remember, this is as x approaches infinity. So you remember our kind of strange way we solve these? Now, one thing is there were some things you could memorize about this so that you should be able to figure this out right now. Remember, when x is approaching infinity, this is where you're trying to find a horizontal asymptote. So there is some 3 rules you can remember so that you could tell me right now what the horizontal asymptote is. And if you remember that, great. But some students did tell me that at university you're going to have to do this the other way. And do you remember what the other way is? You take a look at all the exponents here. So we got a 2 and a 2. And you divide everything by that exponent, x raised to that exponent. So in other words, it's going to be x squared over x squared minus 1 over x squared divided by 2x squared over x squared plus 1 over x squared, which is equal to X squared over x squared is 1. 1 minus x squared, can't do anything there. 2x squared over x squared is just 2, plus 1 over x squared. And then what you have to remember is the special limit we learned, that when you divide 1 by infinity or by negative infinity, it approaches 0. So we have 1 minus 0 over 2 plus 0. We end up with 1 over 2. By the way, remember the fast way to do this? Since the degree of the numerator and the degree of the denominator are exactly the same, they're both 2, right? What you do is you look at the leading coefficients. So you look at this number here and this number here. Well, there is no number there, which means it's a 1. And you just put this one, the 1, over this one, the 2. You get 1 over 2, just like we got there. So that was the fast way of doing that. All right, we'll do this with L'Hopital's rule in a second. Finally, let's try this one. So again, we're going to substitute in. We get the natural logarithm of 1 over 1 minus 1. The natural logarithm of 1, well, that means e to the something equals 1. E to the 0 equals 1, and 1 minus 1 is 0. It's indeterminate. Okay, let's try solving this without L'Hopital's rule. So what would we do? Well, we'd try factoring. No, we can't do that. We would try multiplying by the conjugate. Multiply by x plus 1, I suppose. I'm telling you, that's going to fail spectacularly. It actually turns out you can't solve this. You're stuck. We have no strategy up until today to solve a limit like this. This is where L'Hopital's rule is going to become very, very useful. In these previous ones, it's an easier way to solve it, so that's nice. Easy is always better. But in this one, it's a necessary way to solve the limit. So with no further ado, we better figure out what is L'Hopital's rule. Well, the first thing is it's used to evaluate limits when there's an indeterminate form. So remember those indeterminate forms we talked about, the 0 over 0, infinity over infinity, etc. In those cases, you can use L'Hopital's rule. Suppose we have one of these cases. The limit of f of x divided by g of x as x approaches a equals 0 over 0, or the limit of f of x divided by g of x as x approaches a is infinity over infinity. And this could be plus or minus and plus or minus here. So it could be positive infinity over positive infinity over negative infinity over positive infinity, or negative infinity over negative infinity. Any of these cases. Well, these are just indeterminate forms, aren't they? Where a can be any real number, infinity or negative infinity. So the limit can be approaching any real number, infinity or negative infinity. In these cases, you're allowed to use L'Hopital's rule. And L'Hopital's rule is as follows. The limit of f of x divided by g of x as x approaches a is equal to the limit of f prime of x over g prime of x as x approaches a. So what am I saying there? What does that mean? That means if you want to get the limit of this whole thing, you can find the limit of the derivative of the numerator divided by the derivative of the denominator. So that's not bad. Let's take a look. Let's go back here and try these questions again. So we're going to solve these same questions, but this time we're going to do it with L'Hopital's rule. So this first one right here, we see it's an indeterminate form. We're allowed to use L'Hopital's rule. So what does L'Hopital's rule tell us? It tells us we're going to evaluate the same limit. The limit as x approaches 1. But what we're going to do is we're going to take the derivative of the top here. Just the derivative of the top. Okay, well the derivative of that is pretty easy. It's 2x minus 1 over. Then we take the derivative of the bottom. X squared minus 1. Well, the derivative of that is 2x. And now we're going to hope, won't always work, but we're going to hope that we can now plug 1 in here, substitute 1 in here, and it'll work. So let's try. We'll have 2 times 1 when we plug that 1 in there, minus 1 over 2 times 1 when we plug that 1 in there. 2 times 1 is 2, take away 1 over 2. 2 minus 1 is 1 over 2. We get the answer 1 over 2, which is exactly the same as we got over here. Okay, very nice. Let's try the next one. We try to solve this one by substitution. We end up getting infinity over infinity, which is an indeterminate form. So we're allowed to use L'Hopital's rule. So again, we're going to look at this right here, and we're going to solve it with L'Hopital's rule. So how do we do it? Well, same limit as we started with. The limit as x approaches infinity we take the derivative of the top. Well, the derivative of the top is 2x. We take the derivative of the bottom. The derivative of the bottom would be 4x. And let's try plugging into it. We get 2 times infinity times 4 times infinity, which is just infinity over infinity. Oh, wait a minute. That's an indeterminate form again. It didn't work. Well, if we still have an indeterminate form, you know what you do? You use L'Hopital's rule again. So we're going to use the limit as x approaches infinity, and this time we use the derivative of both of these. The derivative of 2x is 2. The derivative of 4x is 4. So what's the limit of 2 over 4 as x approaches infinity? Well, it doesn't matter what x approaches. This is a constant. It's going to be 2 over 4. So our answer is 2 over 4, which is the same as 1 over 2. And again, that's exactly what we got here. Okay, the last one on this page. Remember, we couldn't even solve this one, but we did find it was indeterminate, so we're allowed to use L'Hopital's rule. So we're going to evaluate this limit again. X approaches 1, but we're going to take the derivative of the top and the bottom. What's the derivative of the natural logarithm of x? 1 over x divided by the derivative of x minus 1. Well, that's just 1. And then all we have to do is substitute in. So we put 1 in here, we get 1 over 1 divided by 1. Well, 1 divided by 1 is 1, divided by 1 is 1. Our answer is 1. That was really not that bad. Okay, I don't even know if this is necessary, but we'll do some more examples. First of all, let's try substitution, because we need to make sure, first of all, you have to make sure it's indeterminate form. If it's not indeterminate form, you cannot use L'Hopital's rule. So if we try substituting, we'd have sine 0 over 0. Sine 0 is equal to 0. So we have 0 over 0, indeterminate form. We're allowed to use L'Hopital's rule. So let's go for it. Keep the limit the same. We take the derivative of the top. The derivative of sine x is cosine x. The derivative of x is 1. And now we just substitute in. So you would have cosine 0 over 1. Well, cosine 0 is equal to 1 divided by 1 equals 1. Next one, we're substituting infinity into here. Now, this is another one that if you know the rules, you can solve this right away. You can see the degree of the top is 3, the degree of the bottom is 3, they're equal. You just take the leading coefficients, which are 5 and 8. So our answer should be 5 over 8. But let's say we didn't know that. If we were to plug infinity into here, you're going to end up with infinity over infinity. It's indeterminate. So let's go straight to using our L'Hopital's rule. So we'd have the limit as x approaches infinity, and we take the derivative. So we'd have 15x squared plus 8x minus 7 divided by 1 minus 12x plus 24x squared. And if you try substituting into there, you're going to get infinity over infinity again. So it's still indeterminate form. Let's use L'Hopital's rule again. So we have 30x plus 8 over negative 12 plus 48x. And if you tried that, you're going to get infinity over infinity again. You got to use L'Hopital's rule again. So the derivative of the top is 30. The derivative of the bottom is 48. That's a constant, so it's just equal to 30 over 48. Put it in lowest terms, divide them both by 6. You get 5 and 8. And remember, it's exactly what we said it would equal, 5 over 8. So a little bit longer than just memorizing the rule, but still works. L'Hopital's rule will always work as long as it's indeterminate form when you try to substitute into the limit. Okay, let's try another one. If we substitute in infinity here, you'd have e to the infinity over infinity squared. Well, e, that's 2.7 to the infinity, that's just infinity. And infinity squared is infinity. It's indeterminate. So we're allowed to take L'Hopital's rule. So there we go. The derivative of e to the x is e to the x. The derivative of x squared is 2x. So let's try substituting in. You get e to the infinity over 2 times infinity. That didn't seem to help much. We again have infinity over infinity. But let's try using L'Hopital's rule again. So in the top, derivative of e to the x is just e to the x. The derivative of 2x is 2. So if we substitute in now, we have e to the infinity over 2, which is infinity over 2, which is equal to infinity. That's not an indeterminate form, that's an answer. Infinity is fine. You just can't have infinity over infinity. So this is fine. Our answer here is infinity. Okay, one more, little bit more challenging here. So we're going to substitute in, see what we get. We get tan 0 minus 0 over 0 cubed. You know what tan 0 is? Tan 0 is 0, so you get 0 minus 0 over 0. 0 over 0 is indeterminate. So we're allowed to use L'Hopital's rule. Okay, so the limit as x approaches 0 of derivative of the top. The derivative of tan x is secant squared x minus the derivative of x is 1 all over 3x squared. So if we try substituting in there, we get secant squared 0 minus 1 over 3 times 0 squared. Secant is the reciprocal of cosine. So what's cosine 0? 1. What's the reciprocal of 1? 1. 1 squared is 1. So we get 1 minus 1 over, this is going to be 0 on the bottom. You're going to get 0 over 0. So this is an indeterminate form. So in other words, we can proceed further. We're going to take a look at this limit right here, and we can take the, and we can use L'Hopital's rule with that. So the limit of as x approaches 0. Okay, we're going to have to use the chain rule here. This is why it's starting to get a little complicated, isn't it? So we got to use the chain rule. The outer function is something squared. So we're going to use the power rule first. We're going to go 2 times secant x times, now we take the derivative of the inner function, which is secant x. What's the derivative of secant x? It's secant x tan x. And then the derivative of negative 1 is 0, so there's nothing to put there. Okay, all divided by 6x. So let's simplify that. We have a 2 here and a 6 there, so we can cancel this and we'll just be left with a 3 there. And we also have a secant x and a secant x. So we have secant squared x tan x all over 3x. Now I will tell you that if you try plugging 0 in here, we already know what secant squared 0 is. We did up here, we got 0. So you're going to have 0 over 0. It's an indeterminate form again. And at this point, you might just give up. You'd be like, I can't do this. It's too hard. But there's another strategy to take here. When you have these trigonometric ratios, what do we often do with them? We make sure that they're all in sine and cos. So this is the strategy that's going to have to take place here, which I know is a little bit of brilliance to figure that out, but that's what you're going to have to do. So what we have here is secant squared, which is the same as 1 over cosine squared x, and then we have tan x, which is sine x over cosine x, and this is all over 3x. So the other way you could write this is sine x over, could combine these together, right, and get cosine cubed x, and we divide by 3x, that's also going to be the denominator. This is the same as, right, this dividing by 3x is the same as multiplying by 1 over 3x. So this 3x ends up the same denominator as the cosine x. So we're going to have 3x cosine cubed x. And again, you might be looking at that and being like, I just have no clue. I don't know what to do here. But here's the key. Do you remember this? Sine x over x as x approaches 0. This was something we learned about, this limit right here, a very important limit. Coming back to you a little bit. So in other words, another way I could write this is the limit as x approaches 0 of sine x over x times 1, there's nothing else left on the top, times 3 times cosine cubed x. And we know that this part here in yellow, right there, what does that equal? That equals 1. So when now we can actually evaluate this. And what we're going to get is 1 for that part, and then we'll substitute and pray it doesn't equal 0 on the bottom, and we get 1 over 3 times cosine cubed of 0. We've already talked about what cosine 0 equals. Cosine 0 equals 1. 1 cubed is 1. 1 times 3 is 3. So we get 1 times 1 over 3, which is equal to 1/3. And that is our answer. So again, this last one's very difficult. You'll find a lot of these L'Hopital's rule are not so difficult at all, but yeah, I would say the trigonometric ones can be, as always with trigonometric stuff, can be more difficult, so watch out for those, and get familiar again with this limit right here. That'll show up again, that sine x over x as x approaches 0. which equals 1. One last thing, make sure when you're doing these questions that it's an indeterminate form before you start using L'Hopital's rule. You can't use L'Hopital's rule if it's not an indeterminate form. It has to be 0 over 0 or infinity or something like that when you try substitution in the original question. Okay, good luck everyone. You lose every